Okay guys, so this is your video content for 10.5, which is about radicals as exponents. So first things first, we should probably try to remember how exponents work. So 10.5, Rudy deals as exponents. Okay, so first things first, let's recall that for this lecture, let's just assume x is bigger than or equal to 0. This is really just to deal with plus and minus issues with even powers. It doesn't matter most of the time. Don't sweat it most of the time. I'm just going to assume x is bigger than 0 for now. And I'm going to assume that I've got some number n and some number m that are natural numbers, so counting numbers, right? And let's just recall how exponents work. If I've got x to the n, that means I want to take x and multiply it by itself n times, right? Okay, so really this is just kind of our basic rule, and this forces a couple of things. So if I take x to the n and multiply by x to the m, I get, let's see, first there's n x's from x to the n. They're all multiplied together, so there's n of these. And then we're multiplying that by more x's, specifically m of these. So all told, we've got n x's and then m more come along. That leaves me with x, the n plus m, because this whole group is n plus m x's multiplied together. You guys all remembering this, hopefully? Okay. There's another rule that we should remember, which is that if we have x to the n and raise it to the m, that this is, let's see, so doing that outside exponent first, that means I've got x to the n multiplied by itself m times. And so there's m of these. And then I can expand these guys, and they're made of n of these, right? And then we're multiplying n more for the second one. So here's n more, and then we're going to keep doing that, and then we're going to get n more for the last one, and all told there are going to be m groups of these, right? So that should be m groups of n things gives me m times n x's. Okay, so I get this multiplication rule. Cool. All right, so these are the things I need to remember. Now, the basic idea of thinking about radicals as an exponent is just, okay, these rules were nice, right? So I've got these nice rules. I'm going to put them in a box over here. So nice rules say that, okay, x to the n times x to the m is x to the n plus m, and x to the m, n to the m is x to the n times m. So my idea, basically, is just let's force these to work for things that aren't just counting numbers. So what do I mean by let's force these to work? I mean, let's just declare that these rules work and see what we get out of it. So, okay, one thing we might look at is we might look at, okay, the square root of x is a thing that when I square it, I get x back. Remember, I assumed x was positive, so I wasn't dealing with negatives here. So I don't have to worry about absolute value of x or x restricted. Really, this one's x restricted to the positive numbers, right? So I get this. How many x's are here? Well, there's just a 1, right? So if I thought about this as being an exponent, so I might think, okay, this is like x to some k power, and I raised it to the second. So I'm kind of thinking, well, this thing might really be the same as if I did x to the k to the second and got x to the 1. But I know how this works, right? This says I have x to the 2 times k. That's my rule about multiplying from over there, is x to the 1. Okay, now if the bottoms are the same and these two things, right, left and right are the same, that probably means that these two guys are the same. Right? So really I'm getting 2k is 1. Oh, and that tells me k is a half. So what's that saying? That's saying that I could think about, right? So, take home message, obviously here, guys, is that root x is x to the 1/2 power. Clarify that. 1/2 power. Okay? Let me think. So if I did a similar thing with the cube root, let's see, how would that look? Oops, what? So if I did a similar thing with the cube root, I'd think, okay, the cube root of x cubed is x, again to the 1. I might think, okay, this is x to some power, I don't know, w, random letter, right? And I might say, okay, let's see, that means that x to the w cubed is x to the first. That means x to the 3w is x to the 1. That should tell me 3w is 1, which tells me w is a third, right? It's applying the divide by 3 function to both sides. Over here, by the way, I applied the divide by 2 function to both sides. So I got w as a third. That really means that I could add a line here, and that's that the cube root of x is x to the 1/3 power. So if we go back to some of those nasty examples we were doing, so some of our examples in class looked like this. We had, take the cube root of x to the 7th, y to the 5th. Really, we could say this is x to the 7th, y to the 5th, all raised to the 1/3 power. And then we could say this is x to the 7/3 times y to the 5/3. And I know what x to the 7/3 is. 7/3 is 2 1/3. So that's x to the 2 1/3, right? 2 plus 1/3. And y to the 1 plus 2/3. And I can say, okay, that's, using my other rule about addition, that's x squared times x to the 1/3 times y to the 1 times y to the 2/3. And then I could rewrite this in an easier way as x squared cube root of x times y times the cube root of y squared. Cool? So this is how we treat rational, right, roots as rational exponents. So really this works for all of them. So if you want to turn the x to the nth root of x, you can say this is x to the 1/n. And then you can just treat it like you do a regular exponent. Again, we have to be careful when things are even, to disallow negative numbers in there. But if things are odd, life is really good. Cool? So this is really 10.5, and there's some homework on Blackboard, so have at it. The answer to the quiz is the cups are blue. Bye.